Hello, my name is James Wash, and I'm a physics math double major here at Trevecca Nazarene University. I would like to present to you the subject of my senior seminar project for physics, the acoustic levitator. An acoustic levitator uses sound waves to counteract the force of gravity on an object and hold it in place in air without external supports. To do this, I built an acoustic levitator that consisted of four parts: a voltage source, an Arduino, a motor board, and the levitator itself. The voltage source provides the power to the whole acoustic levitation system, and also controls how strong the field of levitation is. The more voltage I provide, the heavier an object can be and still levitate. I will explain why that is later. The Arduino acts as a wave generator, creating the high-frequency square waves that will drive the transducers or the tiny speakers in the levitator. It also has some control functionality to move objects up or down while they are levitating. The square waves the Arduino makes, however, are very small, at most a volt or two in amplitude, not strong enough to levitate anything if we fed them directly into the levitator. So, we feed those square waves into this motor control board instead, which amplifies the square waves to a higher voltage, one that's specified by the voltage source. The amplified square waves are then fed into the acoustic levitator. They drive the transducers or tiny speakers and make the sound waves which can levitate objects. To demonstrate how these sound waves can levitate objects, I've put together a Desmos simulation of the sound waves in the levitator, under a variety of frequency, phase, and temperature conditions. In the real acoustic levitator, the sound waves generated come from a variety of transducers arranged in a bowl-like shape on either end. However, these waves combine together in the air in such a way that we can treat them as essentially a single wave. Indeed, some acoustic levitators just create a single very powerful sound wave. A sound wave is just a pressure wave in the air, just alternating high and low pressure areas that travel through the air. Similarly, these waves in Desmos represent which areas of the air have high pressure and which have low pressure. A higher peak means higher pressure at that point. As the waves from the top transducers and the bottom transducers move past each other, the waves add together, and what we get instead of moving waves is a standing wave, a wave that stands still. The standing wave has areas of constant low pressure called nodes, and areas of high pressure in between them. We can see the nodes on this graph as points where the standing wave crosses the x-axis. When we put a light enough object in the levitator, in the path of this wave, it will rest in a low pressure node, supported by the high pressure air around it, causing it to levitate. Most levitators up until this point have used a single transducer and an acoustic mirror to get waves that will add together or interfere with each other to make things levitate. But this dual sound source approach has several advantages. With a single transducer, the mirror will have to be kept at very specific distances away from the transducer. Otherwise, the waves will not be able to add properly to support an object in levitation. But with two sources, this is no longer an issue, because the timing and output of both can be controlled. In fact, by making the waves out of phase with each other, that is, so they don't perfectly match up, we can cause the nodes in the standing wave to move up or down, and carry levitating objects with them. After I constructed the levitator, I began to experiment with it to see how objects behaved in levitation and what the specific capacities of the levitator itself was. I developed this levitator based on previous plans by the team at UpnaLab, so I already had some idea on how it would perform. One thing that should be noted is that the voltage provided to the levitator directly affects the strength of the waves that the levitator generates. Higher voltages mean stronger waves and higher air pressures and greater forces that can be exerted on levitating objects. Another interesting fact is that the force the levitator exerts on objects is proportional to the object's volume, So an object's density is the only thing that really determines if an object can be levitated or not. The densest thing I was able to levitate was a piece of aluminum foil. By providing a signal of 13 volts into the levitator, aluminum foil is roughly 2.1 grams per cubic centimeter, so levitating it with a 13-volt signal is slightly better than the predicted curve by Upnalab. I was able to levitate both liquids and solids, with liquids demonstrating various interesting properties while in levitation, especially with relation to the pressure-voltage relationship discussed earlier. Once a liquid drop was levitated, its shape would be strongly dependent on the ambient pressure and the voltage fed to the levitator. As the voltage decreased, the drop would become increasingly round and sphere-like, less flattened by the pressure in the air around it. As voltage increased, the droplet would become increasingly flattened by the high pressure, often becoming kind of donut-shaped. At high enough voltages, the air pressure and the force it exerted on the droplet would cause it to start decohering and tearing apart. Water droplets subjected to voltages above 11.5 volts would, with little to no provocation, begin to sputter rapidly, as if boiling, and they would throw many small droplets of water in every direction. This would actually prove useful in finding nodes of levitation around the main droplet, as the small droplets would often be recaptured by the levitation field. But this behavior is not universal across all liquids. I also attempted to levitate 10W40 motor oil. This motor oil would begin to decohere at 8 volts. Instead of sputtering rapidly as the water did, it would suddenly foam and fill with bubbles before popping away into nothing. I believe that because oil is less cohesive and has a lower surface tension than water, it could not stay together at higher voltages and would not behave the same way as water when it started to decohere. I actually wanted to try and mix oil and water together in levitation, but I was unable to find a voltage where the two would both levitate and not fall apart. Another fluid-based experiment dealt with crystal formation. A drop of saturated salt solution was placed into the levitation field and allowed to sit for some time to see if the water would evaporate and leave salt crystals behind, and if so, how levitation would affect the crystalline structure. After just a few minutes, I could already begin to see salt crystals precipitating out of the levitating droplet, settling to the bottom but not falling out of levitation. After several hours, all the water had evaporated, and the remaining salt crystals had precipitated into a torus or donut-like shape, approximately the same shape as the flattened water drop. This torus shape was very brittle and fragile and broke easily, unlike salt crystals formed under normal conditions. Normally formed salt crystals were also typically translucent to some degree, while the levitated ones were totally opaque. I haven't been able to closely examine the crystals under the microscope, but I believe this brittleness and lack of translucency may be due to the levitation causing an increased number of crystal defects as the water evaporated, thus decreasing the salt's strength and translucency. I would also like to talk for a moment about possible future experiments that could be done with acoustic levitation. This levitator is more or less entirely vertical, and can only really support objects when gravity is pulling them down into a high-pressure zone. Therefore, when turned on its side, the levitator can only support very light objects, like styrofoam. However, other models of acoustic levitator have been built and demonstrated that do allow for horizontal support and trapping of particles. This is achieved by placing the sound sources at an angle to each other. The interference pattern that would form would create a pressure grid that can support particles at a wide variety of angles. Up in the lab, the designers of this particular levitator have also created a handheld levitator device that does exactly that. Other possible experiments include high-temperature levitation. One experiment that both I and Dr. Halston want to do one day is to levitate molten glass and rapidly cool it, in order to try and make the glass substantially stronger than it would be otherwise. To do this, we would need to melt the glass while it is levitating, which has several difficulties. The speed of sound changes with temperature, so the location of the notes and where the glass itself is levitating would change as it melted. We would need to find a way to keep the glass stable and levitating as this happened, and we would have to construct a levitator that can not only lift a heavy object like glass, but can also withstand the high temperatures. Another option is to create a manipulative levitator. By using the same technique for phase shifting as we used for moving particles up and down, we can use a grid of transducers to move objects both vertically and horizontally, sometimes whole groups of objects. Such technology has been proposed for medical purposes. Some surgeons have proposed that nanotechnology could be put into someone's body through an injection or capsule, and ultrasonic sound waves could be used to control the nanotechnology non-invasively because ultrasound passes right through the human body. I personally attempted to modify the levitator to manipulate objects using frequency modulation to bring them into contact, but this attempt failed and would likely not prove feasible until transducers with wider frequency ranges are available, and we can connect them with higher resolution frequency generators. Working on this project has been really interesting, and I'm glad I was able to share it with all of you. Have a great day!